Hi everybody, welcome to this section 3.2 video. In this video, we're going to take a look at our first nonlinear models. And our first nonlinear model that we're going to really check out is the logistic growth model. So let's take a look at that. So just to introduce this idea of nonlinear and logistic growth model, let's give a little background about what we've been doing so far. So far, we've been observing models of population growth with the linear equation of exponential growth or decay. dp over dt equals k times p. And so this is what we've been working with, especially in section 3.1. And this is beneficial, but mainly beneficial in the short term. So it does not provide a very accurate model for population when the population itself gets substantially large. Other factors, including like overcrowding, effects on environment, supply and demand for food and fuel can affect population growth. Okay, so different factors affecting population growth. So let's look at a new population growth model, which is a nonlinear differential equation. And just a little quick recap of what linear means. Linear is if a dependent variable is only raised to the first power, and derivatives are not inside of functions or to exponents. Okay, so let's look at the logistic growth model. Let's look at this nonlinear equation. The way it is defined is dp over dt equals p times a minus b times p with an initial condition p naught is at time 0. Okay, so why is this non-linear? Well, let's take a look. If I distribute in P, what I end up with is dP over dt equals P times A minus B times P squared. And so this is non-linear because P is our dependent variable. So our dependent variable P is not raised to the first power. So this makes it non-linear. Okay, it's raised to the second power. Our dependent variable is P, our independent variable is T. So in this logistic growth model, A and B are constants, and this is our setup. So down below is a solution to the logistic growth model. Right here, P of T equals A times P naught over B times P naught plus the expression A minus B P naught times e to the negative AT. So developing this solution takes a bit of work, and it's a good task to handle if you're up for it. But for now, we're just going to use this solution as given. So why is this logistic growth model been proven to be accurate for growth patterns in a limited space? So let's go ahead and look at a visual demonstration of this. So let's go ahead and graph what the logistic growth model essentially tells us. So here we go. We have a graph like this. There's no negative time or no negative population, so we are only just in this positive quadrant. So axis of t, axis of population. And the way this would work is we have a couple conditions going on. So here we would have our initial population. We would have what's called A over 2B or our inflection point, and we would have a carrying capacity of A over B. So essentially, our population is exponential at first, but then it hits an inflection point, A over 2B population, and then it starts to tail off towards our carrying capacity. So let's make a couple notes. Let's make sure we're getting this down that A over B is called the carrying capacity, and it is the limiting population. It's the most our population will be growing exponentially. Okay. And our population, if you notice, has early exponential growth. Early exponential growth. And we have an inflection point at A over 2B. So once we get to A over 2B, our population stops growing exponentially and starts tailing off to the carrying capacity A over B. Okay, so there's a couple observations of the logistic growth model graphically, but here's a good question. Why is the carrying capacity A over B? Why is that? So we're talking about a population growth over time as time goes to infinity. So what we could do here to show this and why this A over B is the carrying capacity, the limit as t goes forever in time, is the limit of this solution. So the limit as t goes to infinity of our solution, A times P naught, B times P naught, plus A minus B times P naught, e to the negative at. So if we take the limit of this solution, getting it from right here, what do we do? Well, what we could do is play around with this a little bit. What I'm going to do is take my e to the negative at, going to move that down into a denominator. So we would get limit as t goes to infinity, a times p naught all over b times p naught plus a minus b p naught all over e to the at. So we're solving a limit, okay? So if I plug in infinity for t, what I get is the limit goes away. I get b times p naught plus a minus b p naught all over e times a times infinity. Well, anything divided by infinity goes to zero. So realistically, this whole expression here goes to zero. E to the infinity is just infinity. And so anything divided by infinity goes to zero. And so what I'm left with is A P naught over B P naught. Well, the P naughts cancel out, and I'm just left with A over B. So that's why it's a carrying capacity as our time goes forever. So that's why that's our carrying capacity. But here's just a setup of logistic growth model and how it helps us predict population growth and population stability. So that's it for this video. Thank you for watching. I'll see you in the next one.